Today we're going to be looking at a different type of bond. We're going to be looking at covalent bonds. So just to review from before, why do atoms form bonds? Well, we talked about how atoms form bonds in order to fill their valence energy levels with electrons. This represents the most stable conformation. Why it's the most stable conformation is unclear. But at any rate, we talked about two rules of thumb. One that we're going to be using more often is called the octet rule. And what that tells us is that the elements that we're going to be dealing with, which are called the main group elements, tend to bond in a way such that each valence shell or valence energy level contains 8 electrons. So most of the elements that we're going to be working with are trying to get 8 valence electrons. Again, that represents a full valence shell. Now there's a few exceptions, and those follow the duet rule. So the duet rule is going to apply to hydrogen, lithium, beryllium. And what that says is that these atoms form bonds to have 2 valence electrons, because this is going to be the first energy level. And the first energy level is full when it has 2 valence electrons. Okay. So a covalent bond is similar to an ionic bond in that it's because atoms are seeking to fill their valence shells. But a covalent bond is when the atoms share their valence electrons. If you recall an ionic bond, the elements totally gave away or totally took the valence electrons. Here, the elements are going to share their valence electrons. And this is just a little picture representation where we have 2 hydrogen atoms and the electron cloud surrounding those atoms. And so when one hydrogen atom forms a bond with another, you get hydrogen gas, or H2. And what's happening is that each atom is sharing each atom's electron around each nucleus. So again, a covalent bond is when the atoms share electrons to form an octet, or in the case of something like hydrogen, a duet. So the word covalent actually means, co means sharing, valent means sharing valence electrons. So what ends up happening is we're looking at water here, and we're looking at a Bohr model of water. So you can imagine water is oxygen, so the middle atom represents oxygen, and there's 6 electrons there, or I'm sorry, 8 electrons, 6 valence electrons, and then these smaller ones are hydrogens, H2O. When the hydrogens and oxygen share valence electrons, then what you can count is in the valence shell for oxygen, you have 1, 2, 3, 4, 5, 6, 7, 8. So that follows the octet rule. And for hydrogen, you have 1, 2. So that's going to follow the duet rule. So again, this is just a different strategy, so to speak, where the atoms are sharing their valence electrons in order to achieve a full valence shell, either an octet or a duet. So when we compare ionic versus covalent bonds, remember an ionic bond is when we're completely transferring valence electrons. So that's where one atom gives its valence electron and the other receives the valence electron. This typically occurs between a metal, so we're looking at the left side of the periodic table, and a non-metal, so we're looking at the right side of the periodic table. So if you're looking at the periodic table and you have an element on the left side forming a bond with an element on the right side, chances are you're going to be looking at an ionic bond. Whereas a covalent bond, rather than transferring electrons, we're sharing valence electrons. And this typically occurs between non-metals. So this includes hydrogen and most of the elements on the right side of the periodic table. So if you have elements like hydrogen and carbon, you're most likely going to get a covalent bond. If you have elements like nitrogen and oxygen, you're most likely going to get a covalent bond. If you have elements like hydrogen and oxygen, you're most likely going to get a covalent bond, and so on. Now, when we're drawing or trying to represent covalent bonds, what we do is we write out the chemical symbol. So here we have carbon, and then we connect the two atoms or elements with a line. So this line here represents a covalent bond between carbon and hydrogen. Another molecule you're going to see a lot is water. So we write out the chemical symbol from the periodic table, and then this line here represents the covalent bond between oxygen and hydrogen. Now, based on what we've learned about electron configurations and valence electrons, we actually can predict how many covalent bonds an element is going to make. So let's take carbon, for example. Carbon has 4 valence electrons. And so in order to achieve an octet, it's going to need 4 more valence electrons. So that's going to give it a full valence shell. If it has 4 and it wants 8, it's going to need 4 more valence electrons. So carbon is going to make 4 covalent bonds. And the example we were just using for representing a bond, this molecule is called methane, and it's a gas. And what you'll notice is carbon makes 1, 2, 3, 4 covalent bonds. Now, the reason for that is that if it forms 4 bonds with 4 different hydrogen atoms, each hydrogen atom has a duet, so a full valence shell, and now carbon has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Let's look at another example. Oxygen. Oxygen has 6 valence electrons. So it needs 2 valence electrons to form an octet. It has 6, it's looking for 8, so it needs to add 2 more. So that means that oxygen is going to make 2 covalent bonds. And that's what we saw with water. This oxygen is forming 2 covalent bonds with 2 different hydrogen atoms. And if we look at the Bohr model depiction of this, the outer shell for oxygen has 1, 2, 3, 4, 5, 6, 7, 8. And while it's sharing with these hydrogens, the hydrogens have 2. So oxygen satisfies the duet rule, the octet rule. Hydrogen satisfies the duet rule. So generally speaking, you can use the periodic table to predict how many covalent bonds an element is going to make. Generally speaking, we're going to be dealing with elements in this area of the periodic table, and then also hydrogen. Again, when we're dealing with these metals on the left side, those are typically going to form ions or ionic bonds. And that's specifically when they're forming bonds with things on the right side. But if we look at carbon, carbon is right here, and we said carbon has 4 valence electrons. The way we can determine that is by starting on the left-hand side and counting 1, 2, 3, 4 valence electrons. But if we're trying to figure out how many bonds is carbon going to make, what we can do is count to where it would have a full valence shell. And we talked about last time, the noble gases have a full valence shell. So how many bonds is carbon going to make? 1, 2, 3, 4. How many bonds is nitrogen going to make? Well, we just have to count to the nearest noble gas. 1, 2, 3. Oxygen, 1, 2. Fluorine, just 1. How many bonds are the noble gases going to make? They already have an octet. They have 8 valence electrons. So they're going to make 0 bonds. That's why they're called the noble gases. They're chemically inert. What that means is that they don't tend to react in chemical reactions. So we can move down the line. Silicon, how many covalent bonds is silicon going to make? 1, 2, 3, 4. How many is germanium going to make? Same thing. 1, 2, 3, 4. So again, I've been saying elements in the same column have similar chemical properties because they have the same number of valence electrons. So they're able to form the same number of bonds, and they react in similar ways. So if we look at, again, phosphorus, how many covalent bonds is phosphorus going to make? 1, 2, 3. How many is sulfur going to make? 1, 2. And so on. Chlorine, just 1. So these patterns become really apparent on the periodic table once you know how to kind of read this. So what I'm going to have you do is answer these questions about 3 different elements: nitrogen, I think it was sulfur, and argon. And what I want you to start to recognize is you know a lot about these elements just based on the things we've talked about recently. And so you can make a lot of predictions about these elements and how they're going to behave only based on their electron configurations and how many valence electrons they have. So I think you should be impressed in how much you can tell me about an element just based on the few things we've learned so far.